Hydrogen expectations and realities. This is Cleveland Jones, Professor Cleveland Jones. This is Paul Taylor, consultant. And this is me, Cavanha. Good afternoon to all. It's a pleasure.
Good afternoon, Cavanha.
Good afternoon.
My friend Cleveland, to produce 1 kilogram of hydrogen, we need 50 kilowatt hour of electricity. Only provocative slides, okay? No comments for a while. Hydrogen is highly explosive. It's a domestic fuel, is very dangerous. It does not burn at a slow rate. And transport of hydrogen is very difficult.
Sure.
And the third and last slide, we might be closer to changing course of climate change than we realize that the peak of greenhouse gas emissions seems to be reaching nowadays. So so we do not need hydrogen, I suppose. Professor Cleveland.
I'm not sure, but yes, there are a lot of things going on at the same time. You brought up a lot of interesting slides because some of the recent trends that we've seen point to just what you were saying. Some advances in climate change metrics that people use, emissions and conversions and so on. And there is reason to be optimistic that we may actually be close, despite the fact that, as we've often said, even here, that, China and India are, of course, great emitters, and they continue to do so. But there is some silver lining to these clouds. And in fact, mostly in some of the developed countries, we've begun to see some really fast growth in alternatives. That's true.
That's true. Perfect. Professor Cleveland, could you start this?
Yes, Cavanha, what we wanted to bring up, what I wanted to bring up, is a three-pronged approach where we look at hydrogen from an analogous situation as if it were oil and gas world, where we have the upstream and the midstream and the downstream. In the upstream, in the production of hydrogen, you pointed out, rightly so, that currently to produce a kilogram of hydrogen is a negative energy proposition. You spend more energy than the content of the hydrogen. But that is because we speak of hydrogen as if it were one molecule is the same as another. And in fact, hydrogen has this very peculiar characteristic where you have to talk hydrogen colors. And the hydrogen colors specify what type of production you use in order to get that molecule. Obviously, we've had black hydrogen produced from coal gasification, gray hydrogen where you steam reform methane, and then you can even capture the emissions, so you get blue hydrogen instead of gray hydrogen. These are all very endothermic. I mean, you use more energy than you put out, but they are alternative methods that we have to consider in an analysis of what is practical, not just of what is energy efficient, because a lot of times efficiency is secondary to making sure that things are practical and you get the energy where you need it, and you get clean energy in a particular process that is very polluting, and that in itself has great advantages. So going down the list, we start talking about pink hydrogen, for example, where people say, hey, there's nuclear energy out there. We can produce hydrogen with nuclear energy. I mean, sure, almost any energy, you use it so you get electricity and then you produce hydrogen. But a lot of times the source of that electricity doesn't make things much better, because right now, if we had more nuclear energy at the base of the energy mix, that would be very helpful. So it would be quite counterproductive to use it to produce hydrogen. But there may be instances where that can be justified. So if we go down even more, people talk about turquoise hydrogen, and I think others call it a different color, but that is a quite different uh, method to get hydrogen from methane. But instead of reforming, you actually use pyrolysis, just like you do in some of the unconventional oils that are produced. That you do pyrolysis on the ore and you extract oil and so on. In this case, you do similar type of process with methane, and you produce hydrogen and a much easier source of CO2 that you can capture. So there are advantages. Process wise, it depends, where you are and what kind of source you have for methane. Um, and then, of course, we haven't spoken too much about white hydrogen, but I don't think we can avoid this conversation. When we say hydrogen, we basically are talking about the hydrogen types that we just discussed. From here on down, the hydrogen is a different source. And even though the molecule is the same, where it comes from makes a big difference, because white hydrogen is natural hydrogen, where you don't produce it, you capture it from underground reservoirs that nature has provided from a variety of processes that go on, geological processes, in some cases slow, in some cases not so slow. And this is very important to understand, because white hydrogen can ultimately really displace everything from black to gray, blue, pink, green hydrogen. Forget it. As you know, I'm so much against green hydrogen. All of these conversions, which are extremely energy inefficient, just to be able to call it green. So I think that from white up is a production of hydrogen that ultimately we will abandon, whether that's in 5 years or 10, after we realize that maybe this is a lot of spinning wheels. But white hydrogen has its source in, for example, catalysis of hydrogen from very deep minerals that are uh, they're occluded, and then the hydrogen is occluded, and then under high pressure and temperature and so on, it gets released, and it finds pathways up into regions, a couple kilometers, where you can actually find that hydrogen in reservoirs, as if there were methane in reservoirs with very good seals, and you can produce that. There are many other sources, water reduction, when you have iron deposits, and the iron gets oxidized, and then the water gets reduced, and then you produce the hydrogen. It's a it's a wrong way chemical reaction, but under high pressure, high temperature, iron ores are present in many aqueous environments that can produce hydrogen. And in fact, many people are now patenting artificial, which is called enhanced production of hydrogen, because they grind up iron ore, and they produce it in controlled conditions where you can increase pressure and temperature and get that same reaction in a controlled way. But nature has done that for millions of years, and it continues to do that in prodigious amounts. And people used to say, no, there's no free hydrogen available. They haven't looked for it. There's many places in the world where there's seeps that hydrogen is being lost to the surface, but there's many where that hydrogen is not lost to the surface. It's preserved in reservoirs, and you can drill into them and produce hydrogen. So that concern that we had about it being energy inefficient Now all the energy you need is to drill a hole into the reservoir. That addresses a lot of those concerns.
But not for high volumes or
Yes, high volumes. I mean, the volumes are inconceivable because the hydrogen that's produced is in gigantic quantities because it's geological process. Iron ore is all over the crust of the earth. The thing is that, of course, most of that is vented because it's not trapped. But there are reservoirs just like oil. Some of it is vented and on the surface, and some is trapped. So we have to redirect exploratory efforts to find that white hydrogen. And then, of course, there's even radiolysis of water because if you're close to radioactive minerals, actually they can split water and produce hydrogen also. So you have another source, maybe in lesser quantities, but in the under the ground, there's tremendous amounts of radioactive materials in certain concentrations next to aqueous reservoirs, and they can split the water, and you get the hydrogen being captured. The oxygen ends up reacting with other things. So there's a lot to be learned. And even after we discover where it is and so on, of course, we'll have to learn how to produce it and so on. But we have the advantage of the oil and gas industry, which has taught us a lot about drilling into the underground and producing things. So this is maybe a very positive side of the equation, but it's not the whole story, of course. Just from production side, this is very positive. Then, of course, you all know that I am a big proponent of gold hydrogen. If you just skip a slide, you'll see that I talk about gold hydrogen because that is a realistic alternative for producing hydrogen with enhanced engineering methods involving microbiological processes where you select organisms and so on, and you inject them in depleted oil and gas reservoirs, which mostly have 60-70% of the original hydrocarbons in there that aren't produced. And they can react with those hydrocarbons. Those microbes can actually produce the hydrogen. And even though that's an extremely inefficient energy production process, you don't care because the hydrogen is produced and the oil and gas that was there, you would never produce it anyway. So even if you only produce a small portion, convert a small portion of those hydrocarbons that are there non-producible, it's still a net gain because they'd be there anyway. So it's ways to think of the production cycle for hydrogen where we have to open up our horizons as to what we're talking about when we say hydrogen, not just the colors, and obviously not even just green, because green, all it means is that you don't have emissions because you compensate those emissions, not because you don't have emissions. Obviously, if you produce electricity, almost any electricity source has emissions. You can compensate them, but that's for me, green hydrogen is fake from the start. It's not even greenwashing. But, regardless, we have to open up our minds and eyes to an even wider production source for hydrogen. So that's what I wanted to put out there.
Professor Cleveland, a consultant, Paul, help me with questions to Professor Cleveland.
Okay.
The first one I have, Professor, Germany loves hydrogen. What type of energy, what type of hydrogen they use?
They haven't gotten all the way down this list. They are talking about green hydrogen because this is the hydrogen that everybody is hyped up about. Unfortunately, the green has a very big appeal. I think we have to be rational. We have to be unemotional about things. And in terms of emissions, hydrogen, of course, does not, when it's burned, when it's oxidized, it doesn't produce CO2. But Paul can talk about that. So it's called green, and it's called non-emissions source of energy. But the main thing that I think we should keep in mind is that hydrogen can be an energy carrier or it can be an energy source. All of these colors make hydrogen an energy carrier. So you're working on very inefficient energetic processes to provide an energy carrier of hydrogen to do things, to use as a fuel, to introduce into industrial uses. That is a very complicated way of using hydrogen. If you look at hydrogen as an energy source, that means hydrogen that comes from the underground, from nature, or from processes that go down, that occur down there. That's a different story, because now you're not talking about an energy carrier. Germany, the developed world, and many, even Brazil, which is talking about producing a lot of green energy, a lot of green hydrogen, because there's a demand for it, so they expect to sell it. I think this, when we look back 100 years from now, we'll see this sharp blip, green hydrogen increasing tremendously, and after 5 or 10 years, I think people will forget about it because there's all these other alternatives.
So
Right.
there is no concern. Sorry, Paul. Please go ahead. This is your
Well,
time.
one of the things I'm going to be covering is distribution. You mentioned that hydrogen is a very dangerous gas. How would you equivalate that with natural gas that's produced?
Look, when we're talking production processes, I think that this being dangerous or not being dangerous is a characteristic of its combustion. Producing hydrogen from underground reservoirs, whether from assisted microbiological processes or white hydrogen that's already been produced by nature, is really not that different than producing methane. You have the same concerns, maybe a little bit more strict, but you're just producing from the underground, piping it, making sure you don't have leaks and so on, and processing. This, I'm talking about the production. Once you leave the wellhead and go on from there, that's a different story. I'm talking about producing it from the underground. That process is not supposed to be a major challenge or a dangerous process. I think from the wellhead onwards is what you can talk about, because yes, I think those challenges are very challenging. The molecule is minuscule. It's very easy to escape, and it has very nefarious effects, for example, on steel, steel cracking and so on. Very difficult to handle. Yes, there's engineering solutions, which we can discuss when you start talking about the from the wellhead on. But the production side, I think, is a dominated process. It's a process that engineering wise we can handle even as easily, I would say, as methane, even though hydrogen is more volatile and so on.
Cleveland, are there concerns about economics or only environmental issues?
I don't think really either. Environmental concerns in any drilling operation where you produce a fuel that is combustible and so on, I think, yes, you have, and you have operating procedures. Those operating procedures that the oil and gas industry has learned to adopt at the excellence levels are sufficient to produce hydrogen safely and very inexpensively. I mean, producing natural gas off, as you've seen in so many instances nowadays, even from shale reservoirs, is not very expensive. The break-even price in some of the shale plays in the U.S. is under $20, and there's all that kind of fracking and so on involved. Imagine hydrogen reservoirs where you basically don't even need to do that. They're reservoirs like methane that are in a reservoir with good porosity, just waiting to be tapped. Yes, there's many others that are not producible, but we're looking at the ones that are. That's what the geologists and the engineers are going to have to do, is pick those spots, and there's no lack of those spots. It's just redirecting our exploratory efforts. Instead of looking for hydrocarbons, looking for hydrogen. The cost is not a concern. Very
because with all emerging technologies, costs are going to be higher than what we're accustomed to, but the economic modeling is going to be exactly the same.
Yes.
Cost of production, the cost of delivery to the consumers. and what those consumers are prepared to pay at the beginning versus what they're prepared to pay in 5 to 10 years' time.
A lot of the green hydrogen that is being talked about and already being commercialized and plans to produce so much of it is around among the cheapest, $4, five, six, and up. You know, this is a kilo. This is very high. We're talking about $1 to produce hydrogen to produce white hydrogen. Similar costs when we get things right for gold hydrogen, because it's basically the same thing, just with slight injection of microorganisms. We have to dominate that delicate process, but the costs are not the concern there. Environmental concerns, not so much with actual dangers, but with not allowing leakage from those wells, obviously.
Cleveland, white and gold hydrogen are only in the research phase. Are
No,
they in
no,
the
there
productive
are
phase with high
no.
volumes to support
Yes, there are
the
commercial
demand?
volumes of white hydrogen. Gold hydrogen is only a pilot that has been done, I guess, in Canada. As I mentioned before, even in Brazil, we have an ongoing research project to produce gold hydrogen from depleted oil and gas reservoirs with injection of proprietary microorganisms, because that is the key. Depleted oil and gas reservoirs are all over the world. If this works, gold hydrogen can be produced, in Russia and Canada, Brazil, Africa, Asia, anywhere, because anywhere you have depleted oil and gas reservoirs, you'd be producing hydrogen. White hydrogen is maybe a little bit more picky, but there's actually more of it. It's just a question of finding it, redirecting efforts. And white hydrogen production is already commercial in several countries, widespread continents. So this is a reality that people used to say, "Oh no, you don't find pure hydrogen in nature because it's so volatile, it goes into the atmosphere." Sure, if you don't capture it, it'll just dissipate and goes into the atmosphere.
And why are not being used widely? I mean, we cannot see.
I think we haven't been aware of it, Kalanya. It's amazing. It's just now the amount of papers being produced as to the geology of the white hydrogen, recognizing all of these processes. Where are conditions favorable for radiolysis of water in significant amounts with seals? Where are there seeps that lead into confined reservoirs? Where are processes that have been going on near what we could consider reservoirs that trap the hydrogen? That is the key. If we don't look for something, we're not going to find it. And even when there were seeps of hydrogen, people said, curious, see, there's seeps of hydrogen. It's just venting into the atmosphere. How come no one thought of thinking, well, if there were to be a seal, it's not going to leak? That's all there's to it.
Okay.
It seems too simple. I don't mean to break it down into that level, but this is what explorationists have to do. They have to adjust from hydrocarbons to a mindset focused on hydrogen. The same way that many geologists are now focused on CO2 storage. People used to say, now we get things out of the ground. Now we have to put CO2 into the ground. Geologists and drilling engineers are focused on a different tack. This is going on right now. We have tremendous amount of geologic CO2 storage. It's not that different. It's just changing your mindset so that you do these things slightly different. And you have the wells, you have the reservoirs, you have the installations up topsides. It's not simple. Oil and gas industry had 100+ years to develop very excellent operating procedures, safe, environmentally responsible. We're not talking about cutting corners.
Okay. You wanted to follow the next slide, or?
Yeah, I think Paul can
Sure.
take it up.
Okay. Well, Color aside, hydrogen is the simplest member of the family of chemical elements, and it's not just the smallest element on Earth, but it's also the lightest. So therefore,
Yeah.
in order to transport large amounts of hydrogen, it must either be pressurized and delivered as a compressed gas or liquefied. So the cost and the best method of delivery are the two most important factors governing the viability of hydrogen as a source of energy. So, for example, a large centrally located hydrogen production facility can produce hydrogen at a lower cost because it is producing more. But it costs more to deliver the hydrogen from the facility to the consumers. Based on some of those points you brought up about the nature of the gas, its purity, we don't want any contaminants getting in there, and its leakage.
Yeah.
But in comparison, distributed production facilities produce hydrogen on site, so the delivery costs are relatively low. But the cost to produce the hydrogen is likely to be higher because the production volumes are much less. Transportation is an issue. Transport today, it's the hydrogen is transported from point of production to the point of use by a pipeline or on the road in cryogenic liquid tankers, or as in gaseous tube trailers. Pipelines are only deployed in regions where there is substantial demand, and I'm talking about hundreds of tons per day, and with a demand that is expected to remain stable for decades, i.e., is the same as any other fuel. Yeah? Liquefaction plants, liquid tankers, tube trailers are deployed in regions where demand is at a smaller scale, or it's an emerging market. Demonstrations of hydrogen delivery via chemical carriers, so for example in barges, are underway in large-scale applications such as the export market. But at the point of hydrogen use, additional infrastructure components are commonly deployed, including compression, storage, dispensers, meters, contaminant detection, and purification technologies. For example, stations being deployed to dispense hydrogen into medium or heavy duty fuel cell vehicles are expected to compress the hydrogen to between 350 and 750 bar pressure and dispense that at up to 10 kilograms per minute. That's quite a lot. So high throughput technologies to meet these performance requirements are currently under development. If we go to the next slide.
Oh, sorry. Is this one? No,
No,
this one?
next one again.
Oh, thank you. Sorry.
So the key challenges to hydrocarbon delivery include cost reduction, yet increasing the energy efficiency. And at the same time, we have to maintain the hydrogen purity and minimize the hydrogen leakage. As Cleveland said, the hydrogen is very flammable, very dangerous gas, so leakage will be a major issue. But the purity of that hydrogen has to remain very, very high. And a lot of research is needed to analyze the trade-offs between the different hydrogen production options and the hydrogen delivery options when considered together as a system. So building a national hydrogen delivery infrastructure is a big challenge, and it will take time to develop, and it will likely include combinations of various technologies. The delivery infrastructure needs and the resources will vary by region and type of market. For example, urban, interstate, or rural infrastructure options are going to be completely different. And these will evolve as the demand for hydrocarbon grows, if it does grow. And the delivery technologies will develop and improve with those. So I'm quite sure that the engineers are all looking at this right now. And lastly, what will be the reaction of domestic urban consumers having pipelines with a highly flammable gas being present in their neighborhoods, along with the compression, the storage, the dispensers, the meters, and the contaminant detection equipment, all in their backyards? Think about the security aspects associated with those kind of facilities. And I'm not talking about security as in terrorist attacks, but how secure is that equipment? How safe is it to have in a neighborhood? For example, one small town in England was chosen for a trial hydrogen energy supply. And even though the residents were receiving their energy supply free, the resistance to having all this unsightly, dangerous equipment in their backyards was almost 100%, and the trial failed. So that's me covering the.
Paul, how do you mentioned about infrastructure of hydrogen to transport hydrogen? How do you compare the electricity needs for infrastructure? I mean, can you compare hydrogen and electricity infrastructure? Is too different, or how they are?
Well, on a simplistic terms, the infrastructure for electricity, either via overhead cables, they're safe. Safe in inverted commas, okay? Whereas you need pipelines for hydrogen, and we have the corresponding security.
You mean operational
concerns.
safety, risks of what
Well,
are the risks?
If you're talking about pipelines, pipelines need to be maintained. They need to be secure against any kind of vandalism, but also
Electricity too.
electricity too. But electricity cables are not so easy to damage or be damaged as pipelines are. And also, they don't have the degradation that pipelines will have with the gas or the liquid inside. And if you're transporting by road, you've got to take other factors into account, such as road accidents, delays, everything. It's quite a dynamic situation. And you can have these cryogenic trucks delivering. These are only small amounts of hydrogen gas. Mm-hmm. So you need a very good logistical supply chain management system.
Yeah, but Paul, we will not electrify everything. So we need to have different energies and transportation and ways to transport energy from one point to the consumers.
Yeah.
How do you see hydrogen in this context?
For me, at the moment, hydrogen is still in its experimental phase. It's something that's being considered as a replacement for another energy source, in my mind. It's not going to be the energy supply.
Yeah, Paul, I think some of this has to do, again, with some of what we spoke in other programs. When we talk about future of energy and transition and so on, we have to talk about the short or medium term and then the very long term, because the same reasons that we say that nuclear is not going to carry us anywhere in 5 or 10 years because it just can't be built fast enough. The same thing applies to hydrogen. If it takes 5 or 10 years until engineers can find engineering solutions for some of the challenges leaks and degradation of pipelines and steel and so on. If it takes 5 or 10 years, it can take 5 and 10 years, but maybe after that period, we can start thinking, well, it can have its place in the energy mix because by that time we have the production worked out and we have some of the challenges in transportation and storage and so on, which right
But
now I agree
but
they're
Cleveland,
very big.
Yeah,
but
can I just
Cleveland, nuclear goes to electricity, so it's different from hydrogen that you move the molecule to another
Yeah.
place.
No, the challenge is very big. No question about it. That's why I'm giving it 5 or 10 years. It's not going to be
Yeah.
overnight.
But you've also got to take into account the public perception. What antipathy do they have to a new kind of fuel, especially one that they're going to perceive as being dangerous and has a lot of ugly equipment sitting
People
around
are
there.
against wind farms offshore just because
Yeah.
they look bad. They're against
That's
them
right.
because they can kill birds, which they don't kill too many
That's
birds.
right.
Yeah,
You
that's
know,
right.
so this not in my backyard syndrome is absolutely pertinent for any new energy source. And when
Yeah.
we talk about, nuclear is going to come back, we're going to face the same thing. If we talk about hydrogen, they're going to talk about the same thing. We don't want tanks nearby, even if in 5 years we can say they're very safe, which right now we can't. We have to hedge a bit. This is
Electricity stations. We do not want to be very very close.
even yeah. People don't want to be near a transformer, for crying out loud.
No. And they don't want their house located under a pylon because they can show that the electricity field around those pylons is having an effect on people's mental health.
Exactly.
Yeah. Well, I think some of this is very pertinent because, in fact, hydrogen has a lot of environmental concerns that people are not talking about, which I think we have to bring up. But I'll bring that up when we talk about uses. But Paul is right. The infrastructure needed is right now not as resilient to the kind of damage, whether induced or accidental, that power lines are. Even if we talk about power lines in California, they sag in the heat. Okay, we're already finding solutions for that. Lightning bolts and so on. All of those things are real. Engineers can find solutions to almost anything, but it takes a while until those solutions become economically feasible.
And it's not going to be a be all one all solution, because if you're talking about pipelines in Alaska versus pipelines in the Sahara, you have different environmental impacts on the metals and on the gas that those pipelines are transporting.
Yeah. Paul, I don't know if I can bring up, for example, some of the concerns in terms of uses, because I think, again, there's positives and negatives. Don't mind the birds. In
No problem.
terms of hydrogen use, that I think could be beneficial if we get to the point where we can find solutions and
Birds.
take care.
The birds are listening to your speech about the H2 and they are crazy.
I don't think they like it. I think they're on
Are
13.
they agreeing with you or disagreeing with you?
But the reality is that some hydrogen uses, industrial, can have a very positive effect if you can bring that hydrogen safely and economically into three main industries. Let's just talk about steel, cement, and refineries. Together, over 20% of energy
Good
use,
point.
and you can use hydrogen in a very efficient way in those industries. In fact, with higher quality products in steel, in cement, and in
So you
refining.
mean not using hydrogen for final clients, for people,
No,
but for
using it as
industries?
an industrial energy input of the process, because in steel, of
Generate
course,
electricity.
yeah, in steel, you can decarbonize with hydrogen more efficiently. In cement, you can obviously burn hydrogen with less emissions, and steel is a big emitter. In refineries, it's essential. So if you are able to produce and transport more or less efficiently in those industries, you can have a scale of use where you can say this can make viable an energy economy, even if we're talking 20 or 25% of the energy use in the world, because China, India, the developed world all need steel, cement, and refining, petrochemical industries.
And what's the reason that Germany loves hydrogen? What's the logic of this?
I think it's ideological, related to energy transition and reducing emissions. Any time that you can say it's hydrogen is green because the emissions either have been compensated or they were produced with wind energy or something like that. It's attractive from the point of view of saying that it has no emissions. That is, I understand that argument, and it has a place, and it's very important. I don't mean to belittle it. It's just that I think that there's so many other ways to make that green transition.
But also, with Germany, there's that political side of it where they want to reduce their reliance on Russian energy sources.
Oh, that's right.
Yes, Paul.
Nord Stream exploded.
Ironically, to produce the hydrogen, they're going to need a lot of energy, but they choose their path.
Yeah,
that's right.
true.
And they closed the three nuclear plants, the last three ones.
I mean, like shooting yourself on the foot. And the other thing is, the major uses for when we talk about hydrogen as a fuel, in motor fuels and so on, even though people like to talk about that, I think that it is sad that people automatically think of a fuel as a fuel for a car or a truck, maybe for a ship, maybe for some other uses, but not for those uses. And it all gets dumped into the same pot and say, oh, it's a fuel. Now we have to use it in cars and everything. It just doesn't make sense. And we can go into a lot of the details, but unfortunately, that's how people are addressing it. And I think it's going to be a cold shower that they're going to take in a couple of years when the realization sets in that, hey, hydrogen is not for that.
No.
Yeah. You sent one slide more. You wanted that type.
Yeah, maybe, what I said, hydrogen as a motor fuel, forget it. In the steel, cement, and refining industries, quite important. But I want to bring up something which is very concerning. And hydrogen does not produce emissions that are CO2 related, but it does have a very important global warming potential, GWP. And it is something like over 10, 9 to 14 is the closest that we're seeing in the literature in relation to CO2. Why? Because even though it doesn't produce CO2, it makes it very difficult for the atmospheric CO2 that is in the atmosphere to get degraded and its lifetime thus be reduced. And so hydrogen is an indirect greenhouse gas. When the Germans figure this out, they'll have to rethink about green hydrogen, because the problem is not all hydrogen gets used. There is a very large amount of seeps and leaks and so on. And just because it's a small molecule, it's much worse than methane, which is already difficult. And we have now satellites discovering mega methane leaks all over the world, which we didn't even imagine. And we're coming to the realization that gas, which is supposed to be so much better than oil and so on, is prone to giant leaks in many places. And some countries are of course much worse: Russia, Iraq, Iran. But those are realistic problems. The leaks from installations, from production facilities, as far as methane is concerned. Anytime you have pumping stations, anytime you have a transfer of fuels, you have leaks, and those leaks are estimated to be much greater than methane leaks. And when you consider the GWP for hydrogen, that can be a scary scenario unless and until engineers come up with a very good solution. And I think that will take a long time because that is a very, very difficult, if not intractable problem. But I think that we can say that hydrogen is an emissions problem, and we have to tackle it, recognize it, and not make hydrocarbons the villains and hydrogen, an angel, because nothing is black and white.
No. Yeah.
No, that's right.
Excellent. We covered everything about hydrogen. So we
I
have
think so. I think a lot of people are going to be surprised when they recognize that not everything is black and white, and there are many pros and cons, not just in the difficulty in dealing, producing, and transporting hydrogen, but also in its effects. And I think this is something that just is not in
You mean that-
mainstream discussions.
there is truth between 0 and 1.
Yes. It's a reality that has to sink in.
64 shades of gray. Yeah.
Yeah.
Exactly. Thank you so much.
Great.
It was a pleasure
Nice to
having
talk
you
to you guys.
here in this
It was a
podcast.
pleasure. Thank you.
Bye bye.
Bye-bye.
Thank you. Bye bye.